Hey guys, good morning. Back for another video. Today we'll be talking about physical vapor deposition, um, essentially how we deposit metal layers. But before I jump into the notes, I want to apologize yesterday for the video being kind of weird. I hope it doesn't happen again. I don't really know why that happened in the first place. So if it doesn't happen, we'll just assume it was a bandwidth issue or something I did unintentionally. I am almost ready to send back your homeworks. I've got maybe one or two more to grade. As you're working on the next homework set, if you need a couple more days on that one, that would be no problem. Just let me know. Any questions, send me a note. We can set up a video call, or you can ask them in the comments. That's been working fairly well from my perspective. Things have settled down a little bit here. Hopefully I don't have any more screaming children in the hallway. Let's see here. I'm going to go ahead and need to rearrange some files here. Okay. So I'm going to go ahead and switch things around so that the notes, and these are posted already. I'll do that before so I don't forget. Alright. So I hope that I can keep up this time. Alright, so yesterday we were talking about etching. Prior to that, vacuums and plasmas, and so we're slowly building our toolbox of different processes to enable us to build a semiconductor device. And so after you build your devices, right, then you need to connect them together and to have access to the device, right? So you can, move your electrons back and forth between them. And so these conductive paths, you need a conductive material, and so you need a metal. Prior to this, we either grew our material from the substrate, either by oxidation, or we created it from the substrate by doping. We haven't yet talked about chemical vapor deposition, where we can grow additional semiconductor layers. And so this is one of the first techniques where we are depositing something new onto the surface, as opposed to changing what's already there or selectively removing something there, right, say through photolithography. And in metal deposition or physical vapor deposition, we have two general techniques that we'll talk about. The first is evaporation, and we also have sputtering. And these techniques will take advantage of the vacuums and plasmas that we reviewed a couple of chapters ago. Evaporation, in particular, requires high vacuum. So it's done in a vacuum chamber, and this is so that the metal atoms travel in a straight line and have a fairly long mean-free path so that they don't collide on the way and change their trajectory. So you evacuate the atmosphere so that you are unlikely to suffer a collision. And then you are coating with a metal that you that you heat up to increase its vapor pressure. And so you generate more of these liberated metal atoms from the surface that we use to coat our targets with. Okay, so you're at low pressure, and what you want are the atoms in the atmosphere to be the metal atoms that you want to coat with, and so you need to raise the vapor pressure of that particular metal. Now, you don't normally think about metals, right, being in the vapor because we're used to thinking about them at room temperature, and the vapor pressure at room temperature for a lot of these metals is fairly low. Room temperature is not even really on this chart for many of these metals, with the exception, I guess, of sodium, but that's fairly soft. But things that we think of as metals, like gold and silver and aluminum and titanium and nickel, don't really have appreciable vapor pressures, right? Even we're talking about, pretty low, right? 10 to the minus 5, 10 to the minus 6 torr, even at these relatively high temperatures, right? So if you go down to room temperature, it's essentially negligible. And so you're going to increase the vapor pressure, right, as shown here in this chart, by increasing the temperature. And this should kind of intuitively make sense. Remember, those metal atoms are held in the solid by their intermolecular bonds, and we have metallic bonds. So they're held together in crystalline form. The crystals are driven by how densely you can pack metal atoms together. The valence electrons are free to move around that crystal and kind of forms this sea of electron density, or this kind of negative attractive medium or glue that holds those atoms together. So you have this metallic bond. And whether or not those atoms stay in the crystal, right, depends upon if they have enough energy to break that metallic bond. And the distribution of energy in that material is governed by the Boltzmann distribution. And so you have a certain amount of, a non-zero number of these atoms will have enough energy to overcome those intermolecular bonds just probabilistically, right? So even at room temperature, your vapor pressure is not zero. It's just really, really small to be negligible. But as you increase the temperature, right, you're shifting the tug of war, so to speak, right? You're adding energy on the side of thermal motion, and so that shifts the average energy of those atoms to higher values, which means that there's a higher percentage of those atoms that will have enough energy, say, out in the tail of the distribution, to where they could overcome that intermolecular bond, right? And so the distribution is shifting to higher temperatures. More of those atoms have enough energy to overcome the intermolecular bond, and we see that as a rise in the vapor pressure. It can, this chart makes it look less dramatic because the y-axis is on the log scale, right? But you can see for these atoms, these different elements here, right, a difference of, say, 50 degrees can change the vapor pressure by 10 or 100 times. And so you see here that, to get vapor pressures in the millitorr range for a lot of these conductive elements, right, you need temperatures in the range of 1,000, say, to 1,200 C or so. And so these evaporation processes require that you heat the metal that you're trying to coat your surface with to relatively high temperature, right? So you need to place that metal inside of a crucible of some sort, or heat it with a filament or however, but you need to get it to high enough temperature that you can take advantage of an appreciable vapor pressure and produce a relatively reasonably thick coating, right, in a reasonable amount of time. And since this vapor pressure is an outgrowth of the balance between thermal motion and the thermal energy and also the intermolecular bond, um, metals that have a strong bond will have a lower vapor pressure. And this is, the vapor pressure tracks along with the melting point, right? So, before, melting just means that, all of the atoms have enough energy to overcome the intermolecular bond, right? And so it forms a melt, and they can move around. They can they form a liquid, and above a liquid, you're going to have a relatively high vapor pressure. And so if you have strong intermolecular bond, you have a high melting point. You also have a low vapor pressure at the same temperature, right? So say for instance, tungsten has a really high melting point, which means that to get the same vapor pressure, you're going to have to go to a much higher temperature, or at a lower temperature, your vapor pressure is just going to be a lot lower than, say, a lower melting point metal like aluminum. But a typical setup for an evaporation process is fairly simple, right? You need a vacuum chamber, right? It could be as simple as a bell jar like this. You need a charge, that is your metal, to be evaporated, and then you need to heat it to increase the vapor pressure, right? So you might put it in a, say, a resistively heated crucible, something like that. You need to pump it down, right? So we talked about vacuums. So from atmosphere, you would start off with a roughing pump, and then that would get it down to a certain regime. And then if you wanted to go lower, you would need a different design of vacuum pumps. So you might switch over to a diffusion pump. So it might have a cold trap. This would be supported with a backing pump because these are designed to work at low pressure. And so the differential between the pressure in the vessel as it's decreased and the outlet can't be too great, and so you need to actually evacuate the outlet also, so you have this backing pump here, which would be probably similar to this roughing pump. And so the vacuum, it's pumped down kind of in stages with these different pumps, as we talked about in the vacuums and plasmas lecture. And so you are using thermal energy to drive off these metal atoms from the charge, and when they're liberated from the surface, right, they have some thermal energy and they have a random direction. So they're liberated at some random direction, and since you've evacuated the chamber, right, they're just going to proceed in whatever direction that they started at until they hit something, right? And more often than not, that something will be the wall of the chamber or some other thing inside the chamber or your wafer. And so when you're evaporating, you're kind of spraying out metal atoms everywhere, and they're just landing wherever they land and forming a film. So you cover everything inside the chamber when you evaporate metals. And so how fast do you build up coatings? Well, first of all, you need to ask, well, how fast do I eject the mass from the charge, right? So here we have an expression that is developed by Campbell. This is kind of the net result of a couple different assumptions. But you see here the kind of factors that go into the rate of mass loss from the charge, right? So obviously the molecular weight of the atom is going to dictate this, right? Because every time you lose an atom, if it's a heavy atom, you lose more mass. And then you've got some constants in here, Boltzmann's constant, which is reflective of the fact that you are going to be losing atoms from the tail that have the highest energy, and so that the distribution therein is important. The mass loss rate will be higher for atoms that have a higher equilibrium vapor pressure to temperature ratio, right? So we see here that as you go up in temperature, the equilibrium pressure increases, And so I have this relationship between temperature and vapor pressure, right? So we can't forget that buried within this P sub E, this vapor pressure, is a temperature dependence. So you kind of have this dual temperature dependence. And then your mass loss rate is going to be dependent upon the area, right? Because if you, let's say you have a crucible here that has some chamber that has molten material in it, and you're boiling off those atoms, and right, they're only going to come off of this top surface area, right? So that is going to dictate the mass loss rate also, right? So here we're talking about how fast mass is being lost from the charge. And we're assuming that in the crucible we have a uniform temperature, right, which is important because you see how drastically the vapor pressure can change over a relatively small temperature range, right? So if you'd say, you know, the crucible wasn't very uniform and let's say it was being heated from the outside, and around the edges it was 50 degrees hotter than in the middle, then, you know, your calculation would be off because 50 degrees can change this quite a bit, depending, right? These are fairly steep lines. And also that the area across the top of the crucible is not changing, right? You're not consuming your charge to the point where its area is going down rapidly. So it's kind of assumptions implicit in this expression here. So you're ejecting atoms from the surface at some rate. But not every atom that's ejected from the surface of your charge forms a portion of your deposited film. And so the film deposition rate, right, or the growth and thickness of the film at a particular location is dependent on a lot of the same factors that are in the mass loss rate, right? So if you're depositing a heavier atom, then obviously the rate at which you deposit mass is going to be affected because each atom is going to give you more mass. But if you have a denser film, right, then you're going to have a slower buildup of thickness, right, because those atoms are being packed in more densely. You have a faster deposition rate if you have a higher vapor pressure because you're getting more atoms in the same amount of time. You have the same vapor pressure to temperature ratio in here. The area that you have exposed to the charge, well, no, I'm trying to think. Is that what A is? That, I guess it's the same A. Right, if you have a larger charge, you're going to build up faster. And then you have this additional, like, kind of solid angle term, this 4 pi r squared. And that accounts for the relative position of the wafer to the charge, right? So here we're kind of assuming that this is the location on some sphere of some radius away from the charge. But if I just had an arbitrary geometry, I would also include an angle term in there as well, right? Because if I were far away and I had the wafer turned to a relatively extreme angle, then the projected area that is facing my charge is relatively small. But if I have it on a spherical surface, then those angles can cancel out, and I just have this radius dependence here. But you can imagine that the larger that radius is around my charge, right, the smaller the solid angle is that's actually being exposed to that area that is emitting the atoms, and there will be fewer atoms per area per time, and so, right, I see here that as the radius gets bigger, the deposition rate goes down, which can be a good thing, right? Because at lower deposition rates, you actually get better uniformity. But if you look at this deposition rate, you can see there's a fair amount that goes into it, right? And we're making some assumptions here that may not be true all the time with constant pressure, constant area, you know, known radius and angle of our wafer. And so it's relatively difficult to just measure these things, plug them into a formula like this, and predict what the growth rate's going to be, right? To say, I know for a fact I need to run this process for 10 minutes in order to get 100 nanometers of a metal, something like that. And so it's more reliable to actually measure it in situ. This is similar to what we talked about with the oxidation, with the etching. You can get an idea of how fast your process is going, but there's enough variables that it give you better process control if you can measure it. And so for deposition, for evaporation, what you do is you have a quartz crystal plate monitor. So this is, you have basically a tiny quartz crystal that is in the chamber and is being coated with metal. And this crystal sits on, say, a piezoelectric crystal that you can send a varying signal to, and if you have just the right frequency of that signal, right, you'll have a resonance in that quartz crystal. And so you can monitor its vibration and figure out what the resonant frequency is. However, as it's plated with metal, right, the mass of that resonator changes, and so does its resonant frequency. And so you can correlate the change in resonant frequency to the mass change, which then you can back out the thickness change. And so you just have this little resonator in there that gets coded along with everything else, and it allows you to measure how fast you're depositing the metal. And so evaporation is fairly simple, which is a good thing, but you don't always get very good coverage. And this is due to the fact that those metal atoms are just spraying out in all directions, and they just go where they go and they stick where they stick, and that forms your metal film. This does not work very well if you have surface features that have any aspect ratio at all, because let's say that I have a feature like this that is on a wafer, right, and held at some angle up here. Well, I don't have my metal atoms coming straight in parallel to, this well, and so they're going to come in at some angle, which means that part of the well is going to be shaded from direct sight to that metal charge, right? And so atoms coming in a straight line, right? There is no straight line that leads them to be deposited on this side. And so you can get very poor step coverage, right, on this side of the step, reasonable over here. You can decrease this reliability somewhat by heating the wafer and rotating, right? So if I'm shaded on this side, but I rotate this around, then some of the times I'll be shaded over here, right? So I'm going to get more uniform coverage. And if it's hotter, that increases the probability that an atom comes in. It doesn't stick right where it lands, right? It gives it some energy that maybe it can diffuse around a little bit and fill in some of the low spots, right? So heating and rotating can help, and actually what you have in a lot of these cases with these evaporator systems is you have an arrangement like this that's kind of spherical, but it also rotates around continuously during the deposition, right? So you kind of have this planetary motion that helps to increase the uniformity and increase the step coverage. Right, and we know about diffusion, so we have this similar form here that if I increase the temperature, right, I have better diffusion of those atoms around the surface. So I mentioned that you heat up the metal. Well, how do you do that? The simple way is to just use a resistive heater. So that would be, say, some metal filament. Tungsten is a good choice, very high melting point. So you drive a current through a tungsten wire. Inside of that wire, right, you place a rod of whatever metal you want to evaporate. And the wire gets very hot, conducts that heat to the source metal, and evaporates those atoms. it's a simple setup, but you're also, even if you pick a high melting point, you're still going to be driving off some of the atoms of your filament, which is a degradation mechanism. It also means that as you have higher and higher melting points, it becomes less reasonable that their vapor pressures will be much higher than your deposited or than your heater filament. And so you can also heat it inductively, right? So you have a crucible, and it's down here. The crucible is made out of, say, some material, say silicon nitride, something like that, and you have coils that go around it, and you drive an AC current through those coils, and it sets up eddy currents inside of your metal charge, right? So you have an AC, so you have a changing electric field, which induces a magnetic field. That magnetic field pushes, or, well, let's see here, changing current drives a magnetic field that goes in this direction. I might be getting a little mixed up, but that's kind of beside the point, right? When you have a changing magnetic field, changing current produces a changing magnetic field, which induces an EMF, an electromotive force that pushes these electrons around, and they meet resistance in the material, and so you can heat through a crucible in a similar way that you would heat through a wire, by basically moving those electrons around and producing joule heating. However, if I heat up a crucible really hot, right, I'm going to lose some of those atoms. They're going to go into the melt. They're also going to be ejected. So contamination is a problem with the chamber. And so that leads to other ways of heating, i.e. electron beams. So that's here in the middle. If I want to melt my charge but not heat up my crucible, then I can use an electron beam to essentially impact on the charge and create a localized region of hot material, so that I'm not contaminating my charge with metal or with atoms from the crucible, but I am heating it up enough that the vapor pressure increases, right? And so it's fairly easy with a magnetic field. Here we have a filament that's driving off electrons that they're being accelerated and then turned with a magnetic field, right? And so I can actually use that magnetic field to hit one spot or another. I can have several crucibles that I can move around and heat up at different rates. But this electron beam, if we think about, has some liabilities. First of all, remember up here in this expression here for deposition rate, we assumed that we had a constant temperature across the surface and a constant area. Well, if I'm heating up, right, some small region of my charge, it'd be hard to estimate, well, how big is that region that's actually molten? And the temperature is going to be non-uniform, kind of on purpose, right? Because I want the outsides to be cool so that I don't have contamination from my crucible. Also, we don't just get heating from impacts from electrons. We get lots of other stuff, right? One of which we studied from material 680, and that is the generation of X-rays, right? If you have a high-energy electron smashing into an atom, it can transfer that energy to an inner shell electron, eject that electron, it becomes a photoelectron, and then you get relaxation from a valence electron down to that inner shell. The difference in energy between those two energy levels is great. It generally corresponds to an X-ray wavelength, right? So not only am I heating, but I'm also generating X-rays. And so I've got X-rays in this chamber, which can damage my samples. But like I said, I can take this X-ray beam and I can hit it in different crucibles, which is helpful if I want to plate or evaporate different metals without breaking my vacuum. I don't need to move a crucible around. I can just move my electron beam and heat it a little bit differently, which is helpful right? Especially if I want to evaporate an alloy. If I go back up to talk about this vapor pressure curve, this chart with vapor pressure curves, right? You pick a temperature, right? So if I have, let's say I pick, I don't know, 1200, right? Follow that line up. I see that I have titanium at a relatively low vapor pressure. And I go up, okay, there's nickel at, say, 10 times that, go up again. Okay, gold is 10 times that, go up again, right? We have aluminum, silver, maybe another 10 or 100 times. So at one certain temperature, we have much different vapor pressures for different metals, right? And so that's fine if you're evaporating a pure metal. You can just run your crucible at whatever temperature is best for the deposition rate you're going for. But if I were to take an alloy and put it in my crucible, and if that alloy was made of atoms that had significantly different vapor pressures at the same temperature, then I'm going to be preferentially evaporating the lower melting point, the higher vapor pressure atom than the other. So I might start with an alloy of a certain composition, but I'm going to plate an alloy of a different composition because it's going to be easier to evaporate the atom that has the lower melting point and the higher vapor pressure. And so if I want to deposit an alloy, right, of a certain composition, I may need to have two crucibles that I can run at different temperatures, right? Because if I want to have, let's say, the same, like say a 50-50 alloy, but one has 10 times the vapor pressure at the same temperature, well, I'm going to have to run that at a lower temperature, or the second one at a higher temperature, whatever. There'll need to be a relative difference to account for the relative difference in the vapor pressures of those metals. And so I could run them at different temperatures, or conversely, I guess I could run them at the same temperatures and just add a shutter, right? So that I'm depositing a little bit of, say, metal 1, and then stopping, and then depositing a little bit of metal 2, and then stopping, and then so when I'm, instead of moderating the temperature, I'm moderating the time that the wafer is exposed, right? So I could have alternating layers of different metals and then maybe have an anneal treatment at a later point that would enable those two different metals to kind of diffuse in amongst themselves and create the alloy that I'm going for. All right. So evaporation is simple, but it has some drawbacks, right? Meaning that we just talked about step coverage is poor, contamination can be an issue. Also, it's difficult to deposit alloys. And so to address those shortcomings, other methods were introduced, right? Primary of which is sputtering. Sputtering has better step coverage. It has less radiation damage than e-beam evaporation, and you can deposit alloys. It also makes use of plasmas, right? So we see here a recurring theme is that generally if you add a plasma, you can create a better process. More complicated because now you have to manage a plasma, but like we saw last time with etching, plasmas can increase your etch rate or give you, more controllability. In sputtering, what you're doing is you're using that plasma that you generate to create ions that then you can accelerate into a metal target and eject atoms mechanically, right, rather than strictly thermally, right? So you're crashing these ions into your metal target, and just like if you were to, the picture I think about is like a golf ball going into a sand trap, right? So I've got an ion smashing into the surface, and some of those ions, or some of those atoms, or groups of atoms, are ejected from the surface and travel in a straight line, because again, this is under vacuum, and hit wherever they hit. So we're getting atoms, into open space where they can then travel and redeposit. We're just not doing it thermally, right? We're doing it more mechanically with these collisions. And because it's a physical process, it is less dependent on the vapor pressure of a particular metal. So this is good, right? You can generate an RF plasma and do this deposition with insulating material, which tend to have higher melting points, or I think we'll talk about it a little bit later. This is great for alloys, right? Because you can make a target of whatever alloy you want, and then those atoms are going to be ejected in roughly the same proportion that they exist, because you're not relying on vapor pressure. Whether it hits one atom or another is kind of a probabilistic random process, and it's going to happen in roughly the same proportion that they exist in the target. The ions that are used from the plasma are a little bit different than, say, in ion implantation, right? Because remember, in ion implantation, we have an ion gun, then we're accelerating those ions, we're filtering them, they're going down a relatively long chamber, and so they're higher energy, and they're going to implant more deeply. A lot of times that's by design. But that energy ends up being kind of buried down into the substrate. Here, these plasma ions have less energy, which means they tend to be deposited in just the top layers, which actually increases the rate at which atoms are ejected, right? Because the energy is being concentrated in the atoms that are closest to the surface and are most easily removed. All right, something like this, where we have an incident ion that is injecting energy into just this top few layers, and so these atoms have enough energy to be liberated from the surface. The atoms are being ejected from the surface with a lot more energy than they are in an evaporated case. In the evaporated case, remember, we sort of have this tug of war between thermal process and intermolecular bonding. And when a tug of war ends, right, it usually doesn't end with like one team flying off the field of battle, so to speak, right? It kind of ends with one team kind of falling forward just barely, right? So, it's clear which side has won, but they haven't really moved very far from where they started. Whereas, you could think about, I guess, if you had that tug of war set up, and then the sputtering case would be like, I don't know, putting all of those people in an ejection seat or something, or, I don't know. The analogy is breaking down. But, they're being forcibly ejected kind of from the field of battle. And so it's not a matter of, just barely overcoming some force. You have this ion coming in that's just giving tons and tons of energy. And so it's kind of blasting apart the whole thing. And they're flying off into the vacuum to go and deposit somewhere else. So these ejected atoms have a lot more energy than in the evaporated case, which means once they travel through the vacuum and find a place to land, they have a lot more energy to move around, and that leads to better step coverage. And here's the key thing, without having to heat up your substrate. Remember, because the whole reason we didn't want to heat it up when we developed rapid thermal processing and such is that when you heat up the surface, every time you heat it up, you give energy available for diffusion, right? So you go to a lot of trouble to put dopant atoms just where you want them, and you want to minimize the amount of time and the number of times that you heat up your wafer and start to move those around. This sputtering process suffers from, or has a lot of the same dependencies that we talked about when we talked about SIMS, right? This is a similar process. We have ion impacts, and so we have the same issues about yield, right? So that would be, yield is how many ions you get sputtered relative to how many ions you have impacted, right? So 1 to 1 would be 1 ion in, 1 ion out, right? 3 would be 3 ions out for 1 ion in. We see here that yield, right, sort of how many ions we are getting out of our process, is dependent upon the ion energy, right? That should kind of be intuitive, right? The more energy we put in, the higher the probability is that we can eject multiple atoms. The yield also increases depending upon what our ion that we are using to sputter with is, right? So, and we see here that you get a higher yield as your sputtering atom increases, which makes sense. Again, you're putting more energy, right? So whether you put that energy in via the velocity of the impacting ion or in the size of the impacting ion, right? The energy is, kinetic energy is 1/2 mv squared. So you see here, you have this kind of parabolic dependence. Here it's kind of more linear. However, there's the impact of the valence electrons of the target, or the plasma ions, right? And we see here that you actually get the highest yield for noble gases, right? Here is argon, krypton, xenon, and it kind of goes up as you get up more valence and then drops back down, which kind of makes sense, right? I have a larger electron shell as I'm adding more to given shells. Also, it's less reactive, so it's less likely to hit and stick, and more likely to hit and bounce around if it has its octet more satisfied. What else? Okay, you still have a line of sight process, right? So you have atoms that are coming off with more energy that can move around more, but they're still traveling in line of sight. And so moving the wafers around helps with uniformity, similar to the way it was done in evaporation. You can also increase the deposition rate by increasing the plasma density using magnetic fields. We talked about this in the plasma chapter, right? If I have a magnetic field, these electrons and ions are going to be swirling around, right? Which is going to increase the probability of creating more ions through collisions, which increases the number of collisions on our targets and the amount of ions that are ejected out. So you can increase the plasma density, and via that, the deposition rate by using what's called magnetron sputtering, right, where you are increasing the density via these magnetic fields. Okay, here's the last page. Where am I at on time? 42. Okay, not bad. And so sputtering gives you better films and is more commonly used. It's kind of taking over, I guess, the industry. But even so, there are better parameters than others, right? So I have here a figure from Campbell where you can see quality of the coating, right? Whether it's porous or I guess this one would be cracks. There's an optimal combination of temperature and pressure that gives you the best coating, right? So just like in anything else, you can tune it to have the better results. But in general, sputtering is going to give you better step coverage, which is necessary to cover high aspect ratio features, right? And so as devices are getting smaller and smaller, right? They're getting closer and closer together, but their thickness isn't changing that much. So I have smaller devices, but I still have the same thickness, which drives these channels, these interconnect regions, to be narrower and have a higher aspect ratio, which makes it all the more important to be able to have better step coverage to get those metal atoms down in there to cover that high aspect ratio feature. And you can increase, so sputtering is better by its very nature, but you can increase the step coverage by heating, right? The same mechanism we said before. If the surface is hot, it's more likely that atoms are going to diffuse a little bit. However, when you heat the surface, right, you're going to be diffusing everything on the surface. And you can also have energy available for grain growth, right? So these metal grains can be larger if you're heating the surface. If I have a plasma process, right, I have the inherent participation of electric fields. And so I could bias the wafer to provide that electromagnetic attraction that would actually draw those ions into these high aspect ratio features. There's other techniques that you can use. We already talked about in etching using what's it called? Liftoff, right? Where that is actually intentionally taking advantage of the poor step coverage to enable you to selectively remove the metal. But here you can actually do kind of, I guess, the opposite, where you can force it in there by intentionally coating over the top of this, and then increasing the pressure to kind of collapse that film into the high aspect ratio and kind of force it to fill in there. You can increase the likelihood that an atom will travel to the bottom of this feature by collimating those atoms at the beginning, right? So if I have my plasma, say, in this region here, near the target, I'm generating sputtered atoms, right, all along this region, and they're coming off in random directions. But if I have a series of collimating kind of channels here, ones that are coming off at a relatively high angle aren't going to make it through that channel. It's the ones that are coming out straight are going to make it through that channel. And so if I'm selecting for atoms that have a straight trajectory, there are going to be a lot more of them that have the right trajectory to make it to the bottom of this feature. Right? So I can collimate it beforehand to increase the step coverage. And also I could ionize the sputtered atoms, right? So if those atoms are coming off in the region of the plasma, right, there's a probability that they will be ionized too, which means that that'll have that hook that I need, that electromagnetic attraction to kind of pull those in to the surface, right? So this one kind of goes hand in hand with biasing the wafer. Sputtering is not only useful for metal deposition, right? But you could reverse the polarity and use that same plasma to clean your surface, right? So you would sputter from the wafer, not the target, which allows you to remove that initial thin oxide that forms very rapidly on silicon at under atmospheric conditions, right? So if it's exposed to air at all, you'll have a thin oxide layer. And you may not want to deposit metal right on top of that oxide layer, and so you can actually use the sputtering just by reversing the electrical connection to actually sputter that oxide layer off before you deposit. However, that can backfire because you're sputtering atoms off the surface. Well, there's no guarantee they're going to go off and never come back. They could actually redeposit on that surface and be a source of contamination. Also, smashing ions into your substrate can cause damage in much the same way that it did when we talked about ion implantation. Also, my last note here is that if I'm sputtering a film onto a surface, right now I have an interface between two layers, and these layers have different, say, mechanical properties, different coefficient of expansion. If I'm depositing them and I'm heating the wafer, and the metal, say, is cooling more rapidly, I can have expansion or contraction of the various films later on, after I've deposited and cooled everything down. That can actually produce either tensile or compressive stress, which can be detrimental in that those stresses that are baked in can either deform my wafer or actually result in the metal coating peeling off. And so, as if it needed to be any more complicated, right? You'd say, well, I heated it so that I get good step coverage, and then maybe the way that you heat it actually produces these residual stresses, which can cause other problems down the line. So, everything has unintended consequences and knock-on effects, and so, just like anything else, it's more complicated when you actually get into it. But here we're just trying to introduce some of the basics. So that's all I had on physical vapor deposition.